In this lesson, we're going to look at how we can find the area under a curve by using Riemann sums. So we kind of touched base on this a little bit in a previous video, so this is more going to be a recap and then a couple of extra pieces. So here we have a graph that has nice lines, and to find the area under the curve, we can make these simple shapes. So in the red that's colored in red, we have a square, then we have a triangle in blue, we have a trapezoid in green, and we have a triangle in purple. So it's really nice when we have these types of graphs where we can make very nice geometric shapes to find the area of. But when we don't have that and we have curves, we have to use Riemann sums. So here's an example. We're trying to find the area under the curve, so this is what this integral means, from 1 to 5 of x squared. So x squared is our function, and we want to use 4 subintervals, and in this one, we're looking at the LRAM, which is the left Riemann sum. Okay, so all of this was in the video we watched prior, so we're just kind of recapping this. So here I have the graph of y equals x squared. What a left Riemann sum is making these rectangles underneath the curve, starting with the leftmost point as your height. So you can see this blue rectangle has a height of 1. So we're going to use that height times the length of 1. For the red one, we have the height, which is 4, times the length, which is 1. For the green, we have the height, which is 9, times the length of 1. And then we have the height of the purple one, which is 16, times the length of 1. So we're adding all of these together and we get 30. And what we can see from here as well is that there are pieces below the curve that are not part of any of these rectangles. So we have some empty space, here, 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 and here, and here. So what this is really an underestimation of the area under the curve because we're missing out on all of these blank spaces. That's not included in our approximation here. So 30 is a pretty low approximation for what the actual area is under the curve. So we're going to look at the same exact example, but this time the right Riemann sum, which is the RRAM. And this is just taking the rightmost point as your height. So the same blue rectangle, but now instead of using the left point of 1 as the height, we're using 2 as the height. So the height would be 4, so 4 times the length of 1. Then we're using 9 times the length of 1. We're using 16 times the length of 1, and 25 times the length of 1. So we're always using the rightmost point. So we're noticing that we're not using the leftmost height at all. We're using everything from the right. When we look at this is an overestimation of the area, because even though I'm missing a little piece down here, I can see that a lot of the graph is going above the actual curve. So this means that this 54 is a higher value than what it actually is, so that is an overestimation. So we saw that the left Riemann sum, I'm just going to go back for a second, was 30, which is pretty low. And then we look at the right Riemann sum, which is 54, which is pretty high. So somewhere between 30 and 54 would be a better approximation. So a way to get a better approximation would be to maybe use the midpoint Riemann sum. So that's your MRAM. And that's using the middle point as the height for your rectangles. So in the blue space, the middle between 1 and 2 would be 1.5. So the height at 1.5 is 2.25. The distance between is 1, so that's your length. Okay, for the red one, we're using 2.5. So plug it into your equation for x squared. Your y value, which is your height, would be 6.25, and your length is 1. For the green, we're using 3.5 as the x, so we have 12.25 times 1. And for the purple, we're using 4.5 as our x, so that would be 20.25 as our y, which is our height. When we multiply them and add everything together, we end up with 41, which again is maybe not a perfect approximation, but it's a little bit closer than the left or the right. So you can see that there are some pieces that are missing and there are some pieces that are over the graph. So they kind of almost cancel each other out a little bit, and it's getting more accurate. And then the last type of Riemann sum we have is the trapezoidal Riemann sum. And this one looks like it's pretty accurate because there's not that much white space left around. It's not really hanging over and it's not too much under. So with the trapezoidal Riemann sum, we need to remember the area of a trapezoid, which is your 1/2 base 1 plus base 2 times the height. Now the part of this that I guess is a little bit confusing is that normally when we see a trapezoid, we think about a trapezoid looking like this, where your base 1 and your base 2 are the horizontal pieces. But when we're looking at it this way, it's really on its side, kind of. So the bases are going to be the height of the left side and the right side. So when we look at this blue piece, we have 1/2, and then the two bases. So we have the height of 1 and the height of 4. So those are our two parallel bases. And then the height of the actual trapezoid is going to be the distance here. So that would be 1. For the green, we're doing 1/2 times base 1, which is 4, times base 2, which is going to be 9, times the height of 1. And then the green, we have 1/2, and we have 9 plus 16 times 1. And then for purple, 1/2 times 16 plus 25 times 1. And then we add all that together, and we get 42. So when we talk about the different types of approximations, we really only consider the left to be an under approximation if your curve is increasing. If the curve was going to be decreasing, so if it was something like this, and I used the left Riemann sum, I would see that this would end up being an over approximation. So it really depends on, is the function increasing or decreasing? So when it's increasing, I'm just going to write this over here. When my function is increasing, my left Riemann sum is going to be an underestimation. So I'm just going to write under. And if it's decreasing, then my left Riemann sum is going to be an overestimation. Okay, similar to the right Riemann sum. So here, this function is increasing, and it's an overestimation. So I'm just going to put, if it's increasing, then the RAM is going to be an overestimation. If I were to draw this as a decreasing function, and I do the right one, oops, that's really bad here, but we'll see that it's going to be missing spaces, so it's going to be an underestimation. So decreasing function and using the RAM will be a underestimation. For the midpoint and the trapezoidal, we don't really discuss whether they're over or underestimations. They're pretty close to the actual value, so we could see that the midpoint was 41 and the trapezoidal was 42, whereas the left Riemann sum was 30, which is very low, and the right Riemann sum was 54, which is pretty high. Okay, the more rectangles we use, the more accurate this will be. So if I had smaller widths and more rectangles, I would get a very close approximation for the area under the curve. Most times on the AP exam, when you see questions involving the Riemann sums, they're usually presented to you like this in terms of a table. So I actually just did this for you. I just want to kind of show you because I feel like we know how to multiply things together, but I just want to show you what we're multiplying, and then we'll do a couple of problems together. So here, suppose the odometer on your car is broken, and we want to estimate the distance driven over a 30-second time interval. So we take speedometer readings every 5 seconds and record them in the following table. So here we have the time in seconds and the velocity. So use an LRAM, RRAM, and trapezoidal to approximate the distance driven over a 30-second interval. So if I'm doing a LRAM, I'm going to be using the leftmost point for the height. So for the LRAM, here's one interval that I'm using, the interval between 0 and 5. So the height would be 25 and 31. For my next grouping, I would use 31 and 35, where they have a distance between them of 5. Then this would be my next grouping, my next grouping, my next grouping, and my next grouping. So we're starting with the left. We're using 25 and 31. We're using 31. Then between 25 and 31, we're using 25. In the interval from 31 to 35, we're using 31. 35 to 43, we're using 35. 43 to 47, we're using 43. 47 to 45, we're using 47. And 45 to 41, we're using 45. So when we're doing a left Riemann sum, we're not using that last rightmost height value. So I'm just going to go over here and drag this down a little bit. Okay, so here's our LRAM. So we use the 25, the 31, the 35, the 43, the 47, and the 45. We did not use the 41. And they're all multiplied by 5 because the difference between the times each time was 5. Okay, if I want to find the RRAM, that means that I'm using the height from the right-hand side. So when I look at the interval from 25 and 31, I'm going to be using 31. When I do 31 to 35, I'm then going to be using 35. 35 to 43, I'm using 43. 43 to 47, I'm using 47. I'm using 45, and I'm using 40. So in this case, I'm not using the first or the leftmost height value. So again, let's just look at this. Oops, as I'm changing all these colors, sorry, drag it down. So here, again, RRAM starting with the 31, so we're leaving out that 25, that was your first height, and we are including the 41 this time. Okay, and then the trapezoidal is the next one that we're going to use, and we're not using midpoint here. However, if we were going to use the midpoint, we wouldn't actually calculate the midpoint between the points. We would usually be using the middle. So for instance, if I wanted to find the interval between 0 and 10, I'm going to use this value for my height. If I want between 35 and 47, I'm going to use this one as my height, the 43. So in a table, you're going to use what you're given. You're not going to have to calculate the midpoint. The only time you need to calculate the midpoint is if you have a graph, which they rarely ask you to graph anything on the AP exam by making the Riemann sums. So don't worry about that. So then for the trapezoidal, 25 and 31 are going to be the two bases. 31 and 45 is going to be your two bases. 35 and 43 are your two bases. Two bases, two bases, two bases. So if we see what that looks like written out. Okay, so we can see we have the 1/2 base 1 plus base 2 times the height. 1/2 base 1 plus base 2 times the height. 1/2 base 1 plus base 2 times the height. So we put that all together and we get that approximation. Okay, so here we're going to look at a AP problem. So they're giving us a table of values and they're telling us that it's continuous on the closed interval, 2 to 8, and has values that are given in the table. So use subintervals 2 to 5, 5 to 7, and 7 to 8. What is the trapezoidal approximation of this? So what this integral is telling us is find the area under the curve from 2 to 8 of this function. So we're going to use the graph, the table, and in this case, since we're doing the trapezoidal, we know that we're going to have 1/2 base 1 plus base 2. So I'm using this as my first interval between 2 and 5. So my bases are going to be 10 and 30. So base 1 plus base 2 times the height. So the height is going to be the difference in the x's. So that's going to be 3. Then I'm going to add that to the next grouping. So the next grouping, I'm going to start at 30 and go to 40 because it's from 5 to 7. So it's going to be 1/2. Your base 1 is going to be 30. Your base 2 is going to be 40. And then the difference between 5 and 7 is going to be your height. So that's going to be 2. And then we're going to add that to the last interval of 7 to 8. So we have 1/2. Our base 1 is going to be 40. Our base 2 is going to be 20. And then the difference between 7 and 8 is going to be 1. So then if we just put this all together, I'm going to get 60 plus 70 plus 30. So that's going to equal 160. And that's going to be my trapezoidal approximation. And notice that there are no units here, so I don't have to have units in my answer. Okay, and then we're going to do this last problem. So here you have a volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. The table above gives selected values of the rate of change, r prime of t, of the radius of the balloon over the time interval from 0 to 12. The radius of the balloon is 30 feet when t is equal to 5. So that's our initial condition. We don't really need to use that right now, but when we combine this with other parts to a question, that'll be useful at some point. So the question, use a right Riemann sum with the 5 intervals indicated by the data in the table to approximate the integral from 0 to 12 of r prime of t dt. So find the area under the curve from 0 to 12. So let's worry about that first, and we'll read the rest of the question. So we're using a right Riemann sum. So that means when we go to create our rectangles, right, here's our first interval from 0 to 2. Because we're doing a right Riemann sum, we're going to use the rightmost point as the height. So this is going to be 4.0 as my height times my width or my length or whatever you want to call it. And that's between 0 and 2, so that's going to be 2. Then we're going to add that to the next grouping. So between 4 and 2, the rightmost point is 2. So 2.0 times the difference between 2 and 5, which is going to be 3. Then we have the next grouping. So we're going to use the rightmost point as our height. So 1.2 times the difference between 5 and 7 is going to give us 2. Then we're going to use the next grouping, and we're using the rightmost point. So that's going to be 0.6. And the difference between 7 and 11 is going to be 4. And then lastly, we have the last interval using the rightmost point. So that's going to be 0.5 times the difference between 11 and 12, which is 1. Okay, so notice that all the ones I circled, I did not circle the 5.7. So I'm not using the leftmost point because this is a right Riemann sum. So when I go to evaluate this here, I'm just going to do this really quickly. 8 plus 6 plus 2.4 plus 2.4 plus 0.5. This is going to give me 19.3. And because they did give me units here, this is going to be 19.3 feet. So it says, using correct units, explain the meaning of the integral from 0 to 12 of r prime of t dt in terms of the radius of the balloon. So what this means, this 19.3 that we found, which is the approximation of this, what that means is that it is the change in the radius. So I'm just going to put this here. So from 0 to 12, r prime of t dt is the change. Now notice I didn't say rate of change, because rate of change is the velocity, which is the derivative, which is what we're given, that r prime is the rate of change. And they tell us that in the beginning. They told us that it's the rate of change is what we're looking at. So when we go backwards from the rate of change, which is our velocity or first derivative, we're going back to the original. That's kind of like the position or the distance. So when in terms of context of a word problem, in this case, we're talking about the amount of something. So we're calculating the change in the radius, what the actual radius is. Change in the radius. And I'm going to put in feet because it's using my correct units. From t equals 0 to t equals 12 minutes. Okay, and then the last part of the question says, is this an overestimation or an underestimation? So if I look at my y values, which is my r prime of t, they are decreasing, right? I'm going from 5.7 to 4 to 2 to 1.2 to 0.6 to 0.5. So this is a decreasing function. So since it's decreasing, it's going to look something like this, right? It's going down. So that means that if I'm using a right Riemann sum, think back to what I talked about in the beginning, a right Riemann sum is going to be an underestimation, right? Because it's decreasing and I'm using a right Riemann sum. So I'm just going to write that out. And I'm going to say that it is, oops, not an O, an underestimation. And when you're explaining why something is an under and overestimation, you must state something about the function. Like, is it increasing or is it decreasing? So it's an underestimation, and I'm just going to put because the function is decreasing. And we're using RAM. So because the function is decreasing and we're using a right Riemann sum, that means that This would be an underestimation.